Hello everybody. This is a review of the material covered on Exam 2. I apologize for the audio in the background. My son's watching Star Wars while I'm doing this. I didn't really want to wait until late in the evening to do it, to get this to you as soon as possible. First information we're dealing with here is with mass. This is a review of the problems on homework 3, 4, and 5. So make sure that you bring those to the exam. You can use those during the exam, and you also can use your book. Be sure to bookmark in your book the Appendix B and also table 15.1. The mass doesn't change with location, so it's just 10 kilograms no matter where you are. On the moon, also 10 kilograms. In space, 10 kilograms as well. The thing that doesn't change, the thing that does change is the weight. The weight is also known as the force of gravity. So weight and force of gravity is the same thing. It's equal to mg. And in our case, it's equal to 10 kilograms times 9.81 meters per second square. So you find out that the weight on the Earth is equal to 98.1 newtons, because newtons is the unit of force in the metric system. To figure out what the weight on the moon is, what you do is you simply just divide by 6. And so take this 98.1, divide by 6, that'll give you the weight on the moon. And in space, you're weightless, so that would be 0 newtons in that case. The other kind of problems that we dealt with on homework 3, I believe it was conversion of, for example, 30 miles per hour over to something in the MKS system, metric, meters, kilograms, and seconds. So what you do is you look at this, 1 mile, and I'll let you look up the number of meters in Appendix B, and then the number of hours. Sorry, I'm rushing this. 36,000 seconds. And you're going to get a number. Make sure you include your units, meters per second. So make sure you use your parentheses like that. That's what I'm expecting you to see, to show me on the exam. Last part on this page at least is the ability to find the magnitude and direction of the force. That was my son, by the way. And so if you look at the magnitude of the force, that's without the vector sign on it, it's equal to the square of the two components. So it's negative 3 newtons squared. That's R2D2 in the background. Minus 4 newtons squared, like that. The minus sign doesn't really matter because you're squaring these. And so it turns out to be 5 newtons. To find the direction of a two-dimensional vector like this, theta is equal to the inverse tangent of the y component, which is negative 4 newtons divided by negative 3 newtons. That turns out to be 53.1 degrees, but it's in the wrong quadrant. Our vector is off and to the left relative to the xy coordinate system. Like this. This over here tells us in quadrant 1 that is incorrect. So we get an answer that's over here. So we'll have to add 180 degrees to that. I believe that makes it 233, I believe, for the angle if we add that on there. I'm using 3 significant figures right there. Another kind of problem that we've been working on is those dealing with torque, also known as moment. The moment, or torque, is equal to the lever arm times the force times the sine of the angle between these two vectors. So you have a point of rotation, you have a lever arm R, and you have a force F. Theta is the angle between them. It's not always 90 degrees. Not always that, but it is in some of these cases like these two. We start off with a point of rotation. You look at the direction of that. This is positive J, so J is upward typically on our examples. This one is the force is to the right, positive I hat, so that's positive x-axis. So there's R and there's F. Using our right hand rule, fingers in the direction of R, starting from the point of rotation, curling them back toward F. Thumb goes into the page, so it's a minus on the torque. So if we're looking for magnitude, we use this. If we're looking for direction, we use the right hand rule. So if we now put a vector sign on this, we said that it was into the page, so it's minus, and into the page is k hat. And since these are 90 degrees apart, you have the sign of 90 for that part. So if we're just looking for magnitude, it would be R, which is 4 meters, times F, which is 3 newtons, times the angle which between them, which is 90 degrees. So you don't put any signs on this part right here. You're just looking for magnitude. If you do all of this right here, you get 12 Newton meters because the sine of 90 is 1. There's a Newton meter from that part right there. Okay, and so there's a direction, negative k hat, and this is what we would be looking for. This is the moment with magnitude and direction. It's going into the page, but that's the minus sign. The other kind of problems that we dealt with were those involving stress and safety factor. The equation I'll have on the board for that, enter Darth Vader, is safety factor, and that's equal to the yield strength divided by sigma, which is the stress. Now usually in a problem like this, you're given the yield strength that can be found in table 15.1. You're also given the safety factor, typically in a problem. So an engineer would say, you need to be so safe, you need to be like 4, a factor of 4 for your safety factor, a unitless number here. This is in pounds per square inch, this is unitless. This is going to be in pounds, which is our force applied to a structure, for example, just a beam like that, and we're applying a force on it. And it has a radius to it, and that's going to give us what the area is. And here's, typically they don't ask you for the radius, instead they ask you for the diameter. So another equation that will be on the board is that the definition of stress is equal to force over area. So it kind of has the same units as pressure, force per unit area. And then another equation that we'll have is pi r squared, if realizing that A is the cross-sectional area of our rod, and that's equal to pi d squared over 4. Oh yeah, thank you. My son just handed me this picture. Nice. All right, so then plugging this one in right there, and this one in over here, we have that the safety factor is equal to the yield strength, and then for this we have force divided by area. If I'm just solving for this, putting it right there, so it becomes YS. Okay, thank you, sir. Thank you, son. Okay, so the yield strength, and then we pull the area up to the top. The denominator of the denominator is the numerator, divided by force. Now, the area is pi d squared over 4, so let's put that in next. Safety factor is equal to yield strength times pi d squared over 4. Now that 4 can actually come all the way to the bottom as well, giving you that kind of expression. Now the reason that we did all of this is because we're given yield strength right there. We know what the force is, we know what the safety factor is, but the unknown is typically the diameter of the rod. So if you solve for the diameter of the rod, you have to be able to do the algebra steps for this. I'm going to do it all in one step. And, excuse me, it's going to be 4F times safety factor divided by yield strength times pi. Doing this all in one step, square root. So you have to use the amount of pull right there. You'll have to look at the safety factor given in the problem. They will tell you how safe you need to be for a particular project. The yield strength is a number that depends upon the type of material.